three-dimensional geometry. Okay, so as a simple activity as measuring the bound angle in the laboratory, we can prove now the Lewis structure does not represent what the molecule actually is in terms of their shape, in terms of their geometry, because the Lewis structure suggests that you have a flat molecule. The molecule itself is not flat based on the bound angle there. So how do we explain, how do we make predictions about the geometry of the molecule, and based on the Lewis structure, based on electron distribution there? Well, if you look at this is the Lewis structure, the actual molecule actually takes a three-dimensional shape. Now this is something that you will see in organic chemistry on a regular basis. A solid wedge represent this hydrogen is out of this plane. Okay, and this is the plane where we draw the method molecule there. This hydrogen is sticking out of the plane there. This dashed line, or sometimes you see a dashed wedge, it represents the hydrogen is behind the spring. So only these three atoms are on this particular spring. One hydrogen is sticking out, the other hydrogen is on the back. Okay, so this is the three-dimensional structure. This is very much look like a pyramid there. You have a carbon in the center, and then you have four different sides there. And this is geometry. This is what we call tetrahedral. Tetra means four, so you have four different sides of this molecule there. Now, many molecules, covalent bound molecules, will take up different geometry based on their electron pairs, based on their total number of valence electrons surrounding the central atom there. So, based on the pattern of the number of valence electrons that surround the central atom here, in this case, all four are bounding electrons, and when you have lone pair of electrons there, well, we can actually make predictions of what the molecule is going to look like based on the Lewis structure there. So what determines the shape of the molecule there? It's the number of valence electron pairs around the central atom of the molecule. Now we have to, in order to make the prediction there, we have to be able to determine how many electrons are on the central atom, whether they're bounding electron or lone pair electron. So the total number of valence electron pairs around the central atom is the key for predicting the shape of the molecule or determining the shape of the molecule there. So in this case, we know electrons repel with one another. So lone pair to lone pair repulsion is the strongest. Lone pair to bounding pair repulsion is somewhere in between. Bounding pair is the weakest repulsion. So using this particular pattern there, we can draw a Lewis structure for any covalent bounding molecule. Based on the total number of lone pair of electrons on the central atom, bounding pair of electrons on the central atom, and we can determine the geometry. And this is known as the valence shell electron pair repulsion theory. Okay? So in order to predict the geometry of the molecule, you have to be able to draw out the Lewis structure. And the Lewis structure has to be correct. And then based on the Lewis structure, we can make predictions. I will give you some examples there. Now, if you have a central atom, for example, and it has three valence electron pairs, well, we should have four. Okay, we're going to just use three as an example there. Electrons bear negative charge. So the electron pair and electron pair, they will repel with one another. And when you have one central atom that is connected with multiple other atoms there, those electrons that are being used for forming the chemical bond, they're going to repel with one another. And there is only so much space in the three-dimensional world. Each one is trying to get their maximum elbow space. So they can only push the other electrons so much away from themselves before that pair of electrons will interact with the third pair of electrons in this case. So the electron groups around the central atom, the repulsion of the electron groups around the central atom determines the geometry of the molecule there. Okay, so when you talk about the geometry of the molecule, sometimes we're looking at the actual atoms connected with one another. That's what we call the molecular geometry, MG. And sometimes we are only focusing on the number of valence electrons there. We call it electron group geometry, EGG, or sometimes you see the term EPG, or electron pair geometry. So when you're talking about geometry, you have different focus there, and you have different perspective there. So if you're looking at water molecule, for example, okay, if you have water molecule, Now, there are 3 atoms in water molecule. When you're talking about the geometry of the water molecule, molecular geometry of the molecule, you're talking about how those 3 atoms, what are the spatial relationship among those 3 atoms. When you're talking about electron group geometry, you're talking about this bounding pair, lone pair, lone pair. Total of 4 electron pairs surrounding the oxygen. You're talking about the geometry of those 4 groups of electrons there. Okay, so here you're talking about 3 atoms, the geometry of the 3 atoms for molecular geometry, and then the electron group geometry, you're talking about the relationship among those 4 valence electron pairs, 2 bounding pair, 2 lone pair, surround the central atom. So sometimes they are the same, and sometimes they are different. Now, giving you the definition there, electron group geometry, or EGG, that's geometry taken up by all valence electrons, including the bounding pairs and lone pair, around the central atom. Okay. The molecular geometry is the arrangement in space of the central atom and the atoms directly attached to it. So we're talking about molecular geometry, we're talking about the orientation of the atoms. When we talk about electron group geometry, we're talking about the orientation of electron groups, atoms and electron groups. Those are 2 different things there. Okay, so when we look at the geometry for molecules where you don't have lone pair of electrons, everything is used for forming the chemical bond, then that's a situation where the geometry, electron pair geometry and the molecular geometry are identical. So in this case, if you have 2 bounding pairs of electrons, the formula representation, the representative formula would be AX2. A represent the central atom, X represent the terminal atom. Then you end up with what we call a linear geometry. Now, that's the maximum space those 2 electron pairs can have between themselves. And if you push anything more, pushing each other a little bit more than 180 degrees, and then on the other side, they're getting too close to one another. Okay, so when you have 2 pairs of valence electrons, both of them are used for bounding, you end up with a linear geometry. And when you have 3 valence electron pairs, all of them are used in forming the chemical bond, you end up with what we call a trigonal planar geometry. Okay, now these 2 molecules are still 2-dimensional. Okay. In the 2-dimensional world, we have enough space to separate them. So here we have a 180-degree angle, here we have a 120-degree angle. Okay, and then if you have a 4 valence electron pairs, then the molecular geometry and the electron pair geometry would be tetrahedral. Okay, so they are the same there. Because if you look at the orientation of the atoms, the 4 green balls surrounding the gray ball, the black ball, the carbon there, for example, then they have a tetrahedral structure there, 190-degree bound angle. But if you look at the bounding pairs, those are the electrons holding those atoms together. Okay, they also take the same geometry, tetrahedral. Now, if you have 5 pair of electrons, 6 pair of electrons, this is already an exception to the octet group. 5 pairs on the central atom means you have 10 electrons there, 12 electrons there. And then we have what we call the trigonal bipyramidal octahedral, different types of geometry there. Okay. Now, you can see the geometry of the covalent and bonded molecules solely depends on the distribution of the bounding the distribution of the valence electron pairs around the central atom.